Okay, welcome back to the second video of synthetic roots. I'm just going to write that here at the top, and we're just going to do a quick summary. Uh, Synthetic roots. We're just going to do a quick summary right now of the reactions that you guys have to know. So, this is in your textbook, but I'm gonna expand a little bit on what there is in your textbook, just because then you can maybe follow along, maybe remember and go, whoa, I completely forgot we had that reaction. There's lots of different reactions that we can go through. So, what we're going to start with is we're going to start with alkenes. Alkenes. So that's carbon double bonds that you guys hopefully know a little bit about. So there's one way. We can get alkenes and we can make an alkane out of it. So right, we had alkenes, so let's just say ethene. Sorry, I drew too many hydrogens there. So let's just say we have an ethene, and we can get to an alkane, so we can get to ethane. So remember, we had 2, 3, whoa, I'm drawing my hydrogens again. Crazy day today. So basically, we alkenes, and we can get to alkanes. So this is an addition reaction. Addition reaction with H2. But then we had alkenes. We can get to halogenoalkanes. Alkanes. So halogenoalkanes. And then we can get to alkenes. We can get also to dihalogenoalkanes. So 3 different routes here. We can get alkenes to alkanes by adding hydrogen gas. Alkenes to single halogenoalkanes. And remember this one, we had the addition reactions. We had something like HCl, HBr, HF, HI, depending on which halogen we wanted to add. We added in hydrogen no matter what. We don't really care too much about that. But we wanted to add the chlorine, bromine, iodine, or iodine. Oh, that was supposed to be a fluorine right there, sorry. Fluorine or iodine, whichever one we want to add. So alkenes, if the question said something like that, okay, you start with, there you go. You start with propene, and you want fluoro, let's see, 2-fluoropropane. So that to get 2-fluoropropane, what we want to do is we want to add HF. And remember, we can either go through the SN1 pathway or through the SN2 pathway. Or we can go through the SN, we want to add, we can't really go through either of those pathways because this isn't a substitution reaction, sorry about that. But we can add in 2 ways. We can add the H to the end here and the F to the center, or we can add the H to the center and the F to the end. So we can add in 2 different ways. So this is way number 1 down here, F to the center, H to the end, or F to the end, H to the center. And from what basically we went over, right, it's the stability of the carbocation. And in this case, we've got a secondary carbocation versus a primary carbocation. So we know that the fluorine will add to the second carbon, just because it's Markovnikov's rule. If you don't remember that, you can watch over the last few videos, and it'll make a little bit more sense. So we can have a fluoropropane there. So that's one of the reactions, or a dihalogenoalkane. So if we added a halogenoalkane, if we added it, let's say ethene here, let's say we add HCl, we're going to have C, CCl, HHHHH. So that's going to be a product. Or dihalogenolalkane, we're going to have CCCl, Cl, uh, H, 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 and H. So this one we'd add Cl2, or we add Br2, or F2, or I2, and they undergo the addition reactions to form the dihalogenolalkanes. Okay, so I'm just going to erase the structures just because that's an example, so I don't want it to take up any real estate it doesn't need to take up. Okay, so now we've got those three reactions we can undergo. Add H2, add an acid, a strong acid, or add a halogen. And we form either an alkane, a halogenoalkane, or a dihalogenolalkane. From here we can undergo different reactions. So from alkanes, we can form halogenoalkanes, if you guys remember how to do that. And we did that by using a halogen plus UV light. So we had UV light in the halogen. Remember, that was free radical substitution reaction. So it's a free radical substitution reaction. We can form the alkane to the halogenoalkane by just taking the halogen and reacting it with the alkane under UV light. Because remember that caused the heterolytic or homolytic fission. F2 broke up into two F radicals, and we had that's why we said free radical, because this is the radical substitution reaction. So we're substituting the fluorine in for one of the hydrogens that's in there. Okay, so then once we have the halogenoalkanes, from this we can form alcohols pretty easily. Right? We don't know much about their reactivity. That's not necessarily included in the syllabus, but we know that we can react it to an alcohol. So we can react it to an alcohol using hydroxide, dilute, and heat it a little bit. So heated hydroxide, and it can be dilute because we want that water in there. So we can form an alcohol. So it depends on the identity of the halogen to know what alcohol is formed, right? If we had let's give you an example up here. I'm just going to change the color up just because then we could see some of these reactions we undergo. We can have CCl, or we can have CCCCl. So we can have two different reactions. We can either form a secondary alcohol where we get rid of this chlorine and form an alcohol, or if we had a primary halogenoalkane, we can react that to form a terminal alcohol, a primary alcohol versus a secondary alcohol. And it depends on the halogenoalkane. It depends on the identity of the halogenoalkane. So basically you'll be given the identity of the halogenoalkane, or you'll have to do some sort of addition reaction in order to see, we can take a dihalogenolalkane and we can form a diol, which is two alcohols. So if we had carbon, carbon, chlorine, chlorine, we can react it to form carbon, carbon, hydroxide, hydroxide. And that could be useful in some sort of polymerization reaction. We've got a diol now, and diols are very useful for condensation reactions. In polymerization, it's good for polymers, very, very good for polymers. So if you don't know that, we got to review polymers too. So again, that's Unit 10. So from the alcohol, we said that there's multiple paths we can undergo. We can take the alcohol, and we can react it to an aldehyde, or we can react that alcohol to a carboxylic acid. And that was using two different reactants. If we wanted just the aldehyde, we used potassium dichromate in an acidic solution. Or if we wanted the alcohol to a carboxylic acid, we used potassium permanganate in an acidic solution. So it depends on which path we want it to go to. Okay, so that's. I'm just checking my notes to see which one. So carboxylic acid or an aldehyde, or if you have. So this is only if you have a. I'm going to write this right here. A primary alcohol. If you have a secondary alcohol, you can oxidize it to a ketone, and it's using either one of these. You can use any one that you want. It doesn't really matter that much. You can either put KMNO4 or K2CrO4 O7, sorry. CrO7, Cr2O7, sorry, dichromate, Cr2O7 in acidic medium, and you could form a ketone. So that's the reactions that our alcohols can undergo. We could either make a carboxylic acid or an aldehyde and a ketone. So from here, right, we can take some of this carboxylic acid. Once you form the alcohol, you can take some of the carboxylic acid, or some of the alcohol reacted to a carboxylic acid, and some of the alcohol plus the carboxylic acid. So the alcohol plus the carboxylic acid, and we could form an ester. So that's an esterification reaction. So you can take whatever your starting alcohol is, react it to a carboxylic, and then you have ethyl ethanoate, something like that. So this is basically alcohol plus a carboxylic acid with H2SO4, SO4 as a catalyst, and we could form that ester. So okay, there are some of the reactions we can undergo. Then we can also undergo different ones. So let me just erase this really quickly, just to make a little bit of space for the next one, because we can take this ketone and we can go back to being an alcohol. So if you start with a ketone and it wants you to form an alcohol, remember we had reducing agents. You put it in a square brackets with red to say that's a reducing agent, and we had two of them. We had lithium aluminium hydride or sodium borohydride. So we had the two different ones that we can use. Lithium aluminium hydride was the stronger one. Sodium borohydride is the weaker one. And sodium borohydride only works with aldehydes, only works to reduce aldehydes or ketones, whereas lithium aluminium hydride works for carboxylic acids, ketones, and aldehydes. So this one, you can use to reduce more things. This one you could use to reduce less things. So we can take this aldehyde and we can bring him back to an alcohol by again using lithium aluminium hydride or sodium borohydride. And the carboxylic acid we can bring back to an alcohol. But we can't use sodium borohydride just because it can't reduce sodium borohydride. I'm going to write that in a special color to the side. I'll say can't reduce what the pigeon says, can't reduce carboxylic acids. So this one, your only option is lithium aluminium hydride. It's our only option to get back from a carboxylic acid to an alcohol. So okay, I think that's basically a summary of all of the reactions we can do. All the reactions that you're required to know. So right, it all starts from alkenes at the bottom. Alkenes, halogenoalkanes, halogenoalkanes to alcohols using dilute hydroxide, and then alcohols to aldehydes, carboxylic acids, or ketones, depending on if the alcohol is secondary or if the alcohol is primary. Primary forms an aldehyde because, right, aldehydes are always terminal, so they're always on the end, whereas ketones are always in the center of a chain. Aldehydes are always on the end of the chain, in the center of the chain. So there's a different, and they have different reactivity, and we use different things to reduce them and oxidize them. And right, we can't oxidize a ketone. You can't oxidize a ketone, RCR O. We can't oxidize that any further, right? We can't form a carboxylic acid because look at this, just as an example, O, OH, right? Carbon can only form 4 bonds. 1, 2, 3, 4, 5. 5 bonds. Not possible. Not possible. So let's take that off. So that's why aldehydes can be oxidized to carboxylic acid. And we can oxidize this even further, right? We can oxidize this either using K2Cr2O7 under reflux, or we can oxidize, we can just say, you know what, who cares? YOLO. Didn't think I'd ever say that in a chemistry video. But we can just use KMnO4 and oxidize it in acidic medium to a carboxylic acid. So there's multiple ways to get between these. You can oxidize an aldehyde, but you can't reduce. This isn't possible. You can't reduce a carboxylic acid to an aldehyde, not with the reactants that we've learned. You will learn some eventually, don't worry, guaranteed you are going to learn some in organic chemistry in university. But for now, it's not a reaction that we know, so it's not a reaction we have to care about. So okay, hopefully this video summarized all your reactions you need to know a little bit better. I'd recommend if you didn't understand it, just watch it another time. If not, just shoot me an email or somewhere in Google Classroom and we'll discuss it. Alrighty, thank you.